World-famous physicist Lawrence Krauss stops by the Arizona Horizon Set every month for an update on the latest science news. Tonight, big news on what may have happened immediately after the Big Bang. Here now to explain is Lawrence Krauss. And, you know, sometimes I can be accused of being a little, hyperbolic here. Big news, big. This is huge news.
You can't be too hyperbolic about this. This could be one of the greatest scientific discoveries ever. And now I was just thinking, you're going to talk about taxes later. Nothing's certain but death and taxes. Well, now it looks like even more than ever, the Big Bang was certain.
Okay, we're talking about gravitational waves. We're talking about primordial gravitational wave. What are we talking about?
Yeah, it sounds pretty esoteric. But what was just announced today at a news conference, a press conference, and also a conference for scientists, was the discovery of a signal from the Big Bang, a new window back to the beginning of time. We'll have time to work through this a little bit. What the signal were these things called gravitational waves, and we may have to talk about them a little bit. But these waves, we have every reason to believe, for reasons we'll go into, they were generated when the universe was less than a millionth of a trillionth of a trillionth of a trillionth of a second old, and will allow us not just to directly observe essentially almost the beginning of the universe, turning metaphysics into physics, but also explore the properties of the physical universe on energy scales that are 10,000 billion times bigger than the scale of the Large Hadron Collider. So it's an unbelievably massive result. It changes everything. It makes our understanding of the universe now empirical, back to a time that's orders and orders of magnitude before we were earlier able to see. If we look out, we've talked about this before, when we look out at the universe with light, we can only see as far as the light can come from. And I can't see past the walls of this studio. In the early universe, the universe was hot and opaque. And light couldn't get through the plasma of particles. When the universe was about 300,000 years old, matter became neutral and the universe became transparent. So when we look out, we can see that surface, if you wish, where the universe first became transparent. We call that the cosmic microwave background radiation. Radiation coming at us from all directions from that surface, which was originally 3,000 degrees, but is cooled now to 3 degrees. So up to this point, when we want to look back directly at the Big Bang, the farthest we could see was back to a time 300,000 years after the Big Bang. But gravity waves, and we'll talk about them, are so weakly interacting that gravity waves that originate in the Big Bang itself can make it all the way to us. And if we can see them, instead of seeing the universe when it was 300,000 years old, we'll get an image, if you wish, of the universe when it was a millionth of a trillionth of a trillionth of a trillionth of a second old.
Okay, so you're talking about echoes, I guess, of the Big Bang. So how do we know that these gravitational waves existed or started at that infinitesimal time period?
One of the reasons is that the strength of gravitational waves depends upon the energy. I'm creating gravitational waves right now as I wave my hands. Einstein's general relativity said something remarkable. Just like when I shake an electron back and forth, I create electromagnetic waves, which allow these signals to be broadcast so viewers can watch them. Whenever you move a mass up and down, you create literally ripples in space and time. Gravitational waves, which are ripples in space. When a gravitational wave comes through this room, it changes the distance across the room by a very small amount, and in fact it alternately compresses and stretches us in one direction or another. But they're so weak that we can't detect them. We built gravitational wave detectors here on Earth. The biggest ones are called the LIGO detector. There's one in Washington State and one in Louisiana. And it's amazing what they can do. But they still haven't seen gravitational waves. They are detectors that have these two tunnels, each 2 miles across. And when a gravitational wave comes by, it may change the length of one tunnel a little bit compared to the other. Mm-hmm. And they've designed things so you can measure the change in a 2-mile-long tunnel to an accuracy of better than the size of a proton. A single proton, the nucleus. It's unbelievable what they can do. But they still haven't seen gravitational waves because even if you bang neutron stars far away, the signal is so small. In order to create a signal that is big enough to see, you need incredible amounts of energy. And that energy, if you wish, only existed in the very early universe when the universe was so hot and the temperature was so high that violent things could happen.
So basically, because another question for me would be, okay, you see gravitational waves, you found these things, whoop-de-doo. How come it's not a couple of universes or planets colliding 1 billion years or 500,000? How do you know that this...
Well, first of all, we know because we'll talk about how it was discovered in a bit, because it distorts this microwave background radiation, it basically had to have been around before there were stars and planets, because the microwave background was created well before stars, planets, or galaxies existed. So it has to be primordial because it's affected that background. It's distorted the light coming to us from that cosmic microwave background surface. Also, the scale of it, the size of the distortions that are seen are immense. So big that the wavelength of these things exceeds the size of, it's almost the size of the visible universe. And so there's no way that colliding black holes or you or I running into each other very fast can create waves of that kind of wavelength. Not only will the intensity be far smaller, but the size will be smaller. So everything about these smacks of the early universe. But more interestingly, perhaps, our best picture of the early universe, an idea called inflation, which says that at very early times the universe expanded very rapidly due to an energy stored in empty space, if you wish. And that energy eventually decayed and produced all the galaxies and stars we now see, something from nothing, which, as you know, I like to talk about. And that what is equally remarkable is we can make a prediction. That theory explains the nature of the cosmic microwave background, explains everything we see about the universe. But we really needed an unambiguous signal of that theory, inflation. And many people, including myself, have predicted years and years ago that if inflation happened at a high enough scale, the gravitational wave background would be intense enough that it could affect the image seen from the microwave background. And I don't think any of us thought it was going to be that strong. But what's amazing is the signal that's been seen is so strong that it suggests that this inflation happened at a scale called the grand unification scale, which is a scale we would have guessed. When we look at the forces of nature, we have hypothesized that they come together, they all come together to form a single force at a scale that's 16 orders of magnitude smaller than the size of a proton.
Yeah.
If they do, it'll produce the signal that they've seen.
What are we looking at here? Is this
okay, looking at a bunch of lines.
Yes, we are. This looks like a game or something. What is this?
It looks like a game. What we're seeing is when the gravitational waves come through the microwave background, what happens is they'll alternately compress space in one direction and stretch it in another. Well, that will cause the radiation to be more intense in one direction than another. We call that polarization. And a gravitational wave that comes through the microwave background will produce a particular pinwheel-type pattern of polarization changes, just like you see here.
Yes.
And nothing else that we know of will produce that kind of pattern. So what you're looking at, in a sense, is the direct image of gravitational waves stretching space in one direction and compressing them in another. And if this is confirmed, this will be the first direct detection of gravitational waves, which were predicted by Einstein. Einstein's theory developed in 1916.
Okay, real quickly, have these waves always been there and we're just now finding, or are they going to be there again tomorrow?
They were produced in the early universe. They are permeating the universe today, just like the microwave background is, and they'll continue to exist. They'll get weaker and weaker as the universe expands, but they have been, because they're the only things that could permeate that plasma, if you wish.
Yes.
They're the only things that really could give us a direct signal. It's like having a new kind of light. We can't see with normal light. It's like having X-rays, if you wish, but it's better than X-rays because they allow us to go through all of that dense stuff between us and the Big Bang and see right back to the beginning.
It's like a curtain between us and the Big Bang, isn't it? Like
Exactly. And these things get right through the curtain.
Yeah.
They're the only things that can. That's why I've been so excited in studying these things for much of my career for the last 30 years.
So how do you prove this?
Well, it's a good question. First of all, you can rule out all other signals, anything else that could produce that kind of signal. Also, inflation makes various predictions that says the gravitational waves will have a certain strength. They'll have a certain intensity for different wavelengths, which we can try and measure, and it'll also compare their intensity with different wavelengths with the other lumps we see in the microwave background. These are all tests we can do of the fundamental idea, and basically, ultimately, we also, and very importantly, we have to confirm this with other experiments. This is a single observation. And since it could be the most important observation made about the universe in our lifetime, if not in the last century, extraordinary claims require extraordinary evidence, and a single experimental claim should never be trusted. But the good news is there are dozens of experiments, including the Planck satellite up there, which are poised. You see, it's really hard to find something if you don't know what you're looking for. So this happened in 1992 when the lumps in the microwave background were first discovered. Everyone was looking for them, but within months of the time that the COBE satellite discovered them, everyone else was able to confirm it, because once you know what you're looking for, it's easier to find it. So there's dozens of experiments at the South Pole, in space, that are all primed to be able to test this. So we'll know very soon if it's true.
And these were found by a telescope at the South Pole?
At the South Pole. The South Pole is the best place to go next to space, because it's very, very dry and very, very cold. And it's a really good place to look for microwaves, because you're looking for a background that, well, the Earth, that's due to a background of radiation that's only 3 degrees above absolute zero. You want to shield out any noise from the Earth, any heat from the Earth, but also water and things in the atmosphere absorb these microwaves. And so the South Pole, if you're going to do an experiment on Earth, is the best place to go. That is, unless you're someone who has to do it, because then you have to spend the winter in the South Pole. And one of the people on this experiment is a former student of mine who had to winter over in the South Pole, and believe me, that's a difficult thing to do.
Not a lot of laughs on that particular. Okay. How is this like the holy grail of cosmology? I mean, is this a Nobel Prize winner? Is this big?
This is the holy grail. That's why there's so many experiments designed to look for it. The one remaining thing, the smoking gun that would tell us if this idea of inflation was right, was gravitational waves. As I say, I've been arguing that for almost 30 years. And so lots of people were looking for it, and lots of experiments were looking for it, and that's what's surprising, because at least one, the Planck satellite, reported an upper limit. It didn't see anything, and the upper limit is below the level that these people are seeing. So there's some tension. So that's why we have to make certain, well, there are reasons to believe you can make both those results concordant, but it's cause for hesitation, at least, because these are about as big as they possibly could have been and not been seen up to now, and that's amazing. But they've done a very careful job, because they're not dummies. They've been analyzing this for 3 years, because they knew the whole world would be watching when they made this announcement. This is not only a Nobel Prize, but this is a game changer, because it means for those people who like to say, oh, I don't believe in the Big Bang, no one was around, how do you know it was there? This is someone calling to us from the Big Bang. Not someone, but something calling to us. This is seeing the Big Bang, just like seeing the sun. And once we measure it, there's no denying it. And those people who don't believe in the Big Bang can stick their heads in the sand more, but it's way too late.
How do we know, and this is, we're running out of time here, but how do we know that why weren't they distorted? 14 billion years to get here. Shouldn't there have been a bump into something here and there? And
they're so weakly interacting that they basically pass through everything without changing, because gravity is the weakest force in nature. Gravity is incredibly weak. We don't think of that. We've talked about that. We don't think of that because we feel it when we try and jump. But that's because the whole Earth is interacting with every atom in our body. Gravity is 40 orders of magnitude weaker than electromagnetism. And so these gravitational waves pass unimpeded. They are the best messengers from the early universe in the beginning of time. Now we have a window, in principle, the first window, to directly probe that era.
Textbooks going to be rewritten because of this discovery?
Absolutely. Absolutely. Now, I mean, it doesn't change the idea it was a Big Bang, but it makes it empirical. It turns metaphysics and speculation into hard science.
Provided it can be proven.
Provided it can be tested and confirmed.
Yes.
And that's the thing. And what we try and do is continually falsify data to see if it's wrong. We look for every possible reason it could be wrong. And believe me, scientists are going to do that. The competitors of these experiments are going to do that. These people have been doing themselves. They had this result 3 years ago. They've been working on it for 3 years to try and make sure they didn't make a mistake.
Well, I'm really glad we had you on the day that this thing broke.
I mean, this couldn't be better. This is a memorable day in the history of science, and you and I were here to share it together.
All right. Good to have you here.
It's great. Bye-bye.